Hello there everyone, my name is Eugene Kogan and I'm here to talk about proportions in geometry of triangles. So let me first quickly go over the overview of the video, and so we will start with a simple method of proving the existence of the incircle and circumcircle. Then we will try to apply this method to medians and fail, and then later generalize our method to use proportions instead of equality and obtain Ceva's theorem, which will instantly obliterate problem with medians. And finally, I will give you a couple exercises for you to solve, and I urge you to do so because that way you will understand the material better. Okay, so now let's talk about perpendicular bisectors. It is a well-known fact that the perpendicular bisectors of a triangle have a common point. There are many proofs of that, but I have an argument which will be useful for us later. So let's take two perpendicular bisectors, so to AB and to AC. As we all know, their intersection, let's call it X, well, it is equidistant from A and B as well as from A and C. Thus, it is equidistant from B and C and lies on the third perpendicular bisector. So what this means is that X is the circumcenter of the triangle. And here we can notice a pattern which involves the following. So suppose there is a line which contains points such that the first equality is met, and there is another line where the second equality is met. Then their intersection actually lies on the third line, which is the line where the third term here is equal to the first term. So in our case, the third bisector. Okay, so let us go over to angle bisectors of a triangle, and it's essentially the same story. So we know that a point on an angle bisector is equidistant from the sides of the angle. So we know that all three distances from all the three sides of a point of intersection of two angle bisectors also lies on the third one. And so X is actually the in-center of the triangle. So far, our method looks like it can crush anything. But here is a simple task which I do not know a way to solve without some generalizations or complications of this method. So it concerns medians. So okay, well, medians, we will just keep that in mind and try to generalize our argument. So the first thing we notice is that any line going through the vertex of an angle is defined by the following ratio of the distances of a point on the line to one side of the angle and the other side of the angle. So this equality essentially means that this ratio is independent of the point on the line. So if we call the line a bar, then this ratio is a characteristic of a bar, not of the points on a bar. So we can apply this to triangles. So first, take two Cevians in a triangle. Cevian is simply a segment connecting a point on a side of the triangle and the opposite vertex of the triangle. So if we have two Cevians, then if we multiply their coefficients, then we get an expression which is eerily similar to the actual ratio for A and B. Like, it looks almost identical. And so we now can prove a common point theorem, and we can do this in the following way. We have three Chevians, right? And suppose that they have a common point. Then here we have, well, the coefficients of these Chevians, or rather the ratios, as I've called them. If we set all of the points here, here, and here to x, then we will obtain that the product of this ratio must be 1. And this is the implication from the left to the right. And the opposite implication is just as simple. It is sufficient to set x equal to the intersection of two of the Chevians, and then because of this equality, it also lies on the third Chevian. Okay, so now we can proceed to Ceva's theorem, which is a celebrated result, and in many cases it is easier to verify this algebraic equality than to prove the existence of the common point. And its statement is very similar to the last theorem, except that instead of k a bar, we have this ratio. Well, and similarly for b bar and c bar. Okay, so let us prove it. The proof is actually quite simple. We only have to notice that since Ka bar in its definition, it's independent of the point on the Chevian, we can calculate it at A1. And so we obtain that Ka bar is equal to A1C2 divided by A1B2. But A1C2 is actually A1B, so A1C2 is A1B times sinus beta. So it's the enumerator of this fraction. And A1C times sinus gamma is equal to A1B2. Great. So then, if we multiply these three coefficients, then the sinuses actually cancel out and we obtain the expected result. Hence, if this is equal to 1, then this is equal to 1, and then the common point exists. And vice versa. If the common point exists, then this is equal to 1, and hence this is equal to 1. Okay, so now in the light of the Ceva's theorem, the problem of medians is just obliterated by this theorem, because all of these ratios, so these by that, are equal to 1, because obviously A1 is the middle point of BC. So the product is also equal to 1. How nice. And finally, some exercises. So first is, what if you have a triangle, you know two of its sides, and the third one you don't know. But what you need to calculate is the following. So in the triangle, by an angle bisector is drawn opposite to the unknown side, and it splits the side into two segments. And the task is to determine what is the ratio of the lengths of these two segments. And the second exercise is a bit easier, in my opinion. It is as follows. Suppose you have a quadrilateral, and three of its angle bisectors have a common point. Prove that this point also lies on the fourth angle bisector. And answer what does the point represent for the quadrilateral at hand. Now I must thank everybody who watched up until this point. I hope that you have learned something, or you were entertained, or you just for some reason watch the whole video. And so if you like my work, like, and if you like my, voice and videos, you can subscribe. It's free, and it motivates me to do more stuff. So again, thank you everyone who watched the whole thing, and I will see you in the next one. Goodbye.